มนุษย์เราเริ่มตั้งคำถามเกี่ยวกับกลไกการทำงานพื้นฐานของธรรมชาติมาตั้งแต่ครั้งโบราณกาลองค์ความรู้ที่ได้ถูกส่งต่อจากรุ่นสู่รุ่นถูกพัฒนาปรับเปลี่ยนต่อยอดผ่านการค้นคว้าทดลองตั้งสมมติฐานและพิสูจน์ทางทฤษฎีเพื่อให้เข้าใจถูกต้องมากขึ้นฟิสิกส์ทฤษฎีถือเป็นวิทยาศาสตร์พื้นฐานที่สำคัญอันหนึ่งที่อาศัยแบบจำลองทางคณิตศาสตร์ในการไขความลับความเป็นไปของสิ่งที่อยู่รอบตัวเราตั้งแต่ระดับอะตอมไปจนถึงระดับจักรวาลส่วนหนึ่งของผลสำฤทธิ์ที่มนุษย์ทำความเข้าใจธรรมชาติผ่านภาษาทางคณิตศาสตร์คือเทคโนโลยีอันหลากหลายที่อำนวยความสะดวกในชีวิตประจำวันไม่ว่าจะเป็นโทรศัพท์มือถือคอมพิวเตอร์หรือแม้แต่โครงข่ายอินเทอร์เน็ตที่ทำให้โลกอันกว้างใหญ่แคบลงไปเพียงปลายนิ้วสัมผัสยังมีคำถามอีกมากมายที่เรายังตอบไม่ได้ทั้งหมดเกี่ยวกับธรรมชาติซึ่งถือว่าเป็นเรื่องที่ท้าทายและรอคอยให้นักวิทยาศาสตร์เข้าไปค้นหาคำตอบในอนาคตในปัจจุบันบุคลากรของวิทยาลัยเพื่อการค้นคว้าระดับรากฐานถือได้ว่าเป็นส่วนหนึ่งในการค้นหาคำตอบของคำถามข้างต้นผ่านการทำงานวิจัยหลากหลายที่ให้หัวข้อที่ล้ำหน้าวิทยาลัยเพื่อการค้นคว้าระดับรากฐานสถาบันสำนักเรียนท่าโพประกาศจัดตั้งขึ้นเมื่อวันที่ 14 มีนาคม พุทธศักราช 2554 รับรองสถานะโดยสภามหาวิทยาลัยนเรศวรให้สถาบันสำนักเรียนท่าโพสำหรับฟิสิกส์ทฤษฎีและจักรวาลวิทยาหรือ TPTP ซึ่งแต่เดิมนั้นดำเนินการภายใต้จิตอาสาของเหล่าคณาจารย์ฟิสิกส์มาสเตอร์ทัพพาเอียนตั้งแต่แรกเริ่มเมื่อวันที่ 8 สิงหาคม พุทธศักราช 2539 ต่อเนื่องยาวนานจนเป็นสถาบันแห่งการผลิตผลงานศึกษาวิจัยและเป็นอาสมบ่มเพาะนิสิตสาขาวิชาฟิสิกส์ทฤษฎีให้มีความรู้ความเข้มแข็งทางวิชาการจนได้รับการยกสถานะให้เป็นหน่วยงานระดับคณะวิชาอย่างเป็นทางการถือเป็นการประกาศเจตนารมณ์ผลักดันยุทธศาสตร์พิเศษของมหาวิทยาลัยนเรศวรที่จะก้าวเป็นมหาวิทยาลัยวิจัยชั้นนำของประเทศในระยะเวลา 10 ปีที่ผ่านมาวิทยาลัยเพื่อการค้นคว้าระดับรากฐานได้ผลิตผลงานต่างๆมากมายผลงานวิจัยตีพิมพ์ระดับนานาชาติจำนวน125 บทความผลงานวิจัยตีพิมพ์ระดับชาติจำนวน8 บทความงานประชุมวิชาการระดับนานาชาติจำนวน7 ครั้งงานประชุมวิชาการระดับชาติจำนวน10 ครั้งการจัดอบรมเชิงวิชาการระยะสั้นและโครงการบริการวิชาการจำนวน58 โครงการการจัดสัมมนาวิชาการ200 ครั้งคณาจารย์ของวิทยาลัยได้รับรางวัลเชิดชูเกียรติทางวิชาการจำนวน15 รางวัลบันทึกข้อตกลงความร่วมมือกับสถาบันชั้นนำอื่นๆจำนวน13 สถาบันหนังสือและตำราวิชาการจำนวน13 เล่มวิดีโอสอนออนไลน์ผ่าน ETH Channel จำนวน34 วิดีโอนอกจากนี้ SIP Plus Consortium ได้สร้างเครือข่ายความร่วมมือทางวิชาการระหว่างสถาบันฟิสิกส์กว่า 20 สถาบันกลุ่มเครือข่ายพิษณุโลกฟิสิกส์เน็ตเวิร์กได้ส่งเสริมกิจกรรมสัมมนาวิชาการในจังหวัดพิษณุโลกและสถานีฟิสิกส์ศึกษาคือการให้ความสำคัญกับครูผู้สอนฟิสิกส์ในโรงเรียนระดับมัธยมศึกษาให้เข้มแข็งและถ่ายทอดสู่นักเรียนผู้เป็นอนาคตของประเทศที่ผ่านมาวิทยาลัยเพื่อการค้นคว้าระดับรากฐานได้ผลิตบัณฑิตสำเร็จการศึกษาในหลักสูตรวิทยาศาสตร์มหาบัณฑิตจำนวน8 คนหลักสูตรประกาศนียบัตรบัณฑิตชั้นสูงจำนวน10 คนหลักสูตรปรัชญาดุษฎีบัณฑิตจำนวน5 คนผลงานเหล่านี้จะสำเร็จขึ้นมาไม่ได้หากปราศจากผู้สนับสนุนและแหล่งทุนวิจัยอาทิมหาวิทยาลัยนเรศวรสำนักงานกองทุนสนับสนุนการวิจัยสกว.สำนักงานการวิจัยแห่งชาติวช.ก โครงการปริญญาเอกกาญจนาพิเศษคปก.นิวตันฟันด์ศูนย์ความเป็นเลิศด้านฟิสิกส์เทพสถาบันวิจัยดาราศาสตร์แห่งชาติองค์การมหาชนมูลนิธิโทเรเพื่อการส่งเสริมวิทยาศาสตร์ The Abdus Salam International Center for Theoretical Physics ICTP อื่นๆปัจจุบันวิทยาลัยเพื่อการค้นคว้าระดับรากฐานมีคณาจารย์ทั้งหมด 9 ท่านโดยแบ่งเป็นคณะผู้บริหารวิทยาลัย 4 ท่าน 3 ห้องปฏิบัติการวิจัยห้องปฏิบัติการวิจัยจักรวาลวิทยาและความโน้มถ่วงห้องปฏิบัติการวิจัยทฤษฎีสนามควอนตัมและฟิสิกส์พลังงานสูงหน่วยวิจัยฟิสิกส์ดาราศาสตร์และจักรวาลวิทยาเชิงคำนวณจากอดีตถึงปัจจุบันเรายังคงดำเนินการภายใต้พันธกิจสำคัญอย่างต่อเนื่องดังประกาศเจตนารมณ์ท่าโพณวันที่ 8 สิงหาคม พุทธศักราช 2539 เราจะสร้างโรงเรียนฟิสิกส์ที่ดีที่สุดแห่งหนึ่งของประเทศขึ้นที่นี่โดยหวังเป็นอย่างยิ่งที่จะส่งเสริมสังคมแห่งการเรียนรู้จุดประกายเยาวชนและสร้างบุคลากรให้มีความเข้าใจลึกซึ้งเห็นถึงความสำคัญของวิทยาศาสตร์พื้นฐานต่อยอดวิทยาการความรู้ด้านต่างๆให้ก้าวหน้าบนรากฐานที่มั่นคงทางวิทยาศาสตร์ซึ่งเป็นกลไกสำคัญให้ประเทศไทยขับเคลื่อนไปอยู่ในระดับแนวหน้าของโลกในอนาคต
Okay, welcome everyone to the IF Colloquium series, number 11. I'm Nina Dangniam, the head of the Quantum Information Science Lab at IF. So this is a physics colloquium series organized by the Institute of Fundamental Study, or IF, at Naresuan University. And we are a theoretical physics research-focused institute that also have master and Ph.D. programs. And today is my pleasure to welcome Dr. Adrian Chapman. There he is. He obtained his bachelor degree from California Institute of Technology and his PhD from University of New Mexico, working on quantum and classical, thermodynamics and aspect of quantum computing that are related to free and interacting fermions. And after his PhD, he has been traveling the world to do postdoc positions in different continents, first at University of Sydney in Australia, and now at University of Oxford in the UK. Today, he'll be talking about his new work, which I'm really interested in, and that's why I'm very excited to invite him here, on how fermions and quantum error correction have something to do with each other. So please take it away, Adrian.
Thanks very much. Okay, yeah, great. So we can see the slides. Thank you, Ninat. My Great pleasure to be speaking today about some work that I've been doing at the University of Oxford with my collaborators, Stephen Flamia at the Amazon Center for Quantum Computing and the Institute for Quantum Information and Matter at Caltech, and Alicia Killar at the University of Maryland. And this is work that Stephen and I started when we were both at the University of Sydney. And so it's on the archive now. It's this top line paper, 2201-07254. But if you're interested in some sort of further background reading, we also have another sort of preceding paper in quantum from 2020. And our current paper on the archive is in publication with PRX Quantum. So our motivation is essentially error correction. So error correction is going to undoubtedly be necessary for any kind of feasibly scalable quantum computation that can sort of continue unabated for an arbitrarily long time. It's an extremely rich and well-developed field. So I will only sort of introduce the very basics of quantum error correction in this talk, but sort of on the right figure here is a schematic representation of the toric code, which is a stabilizer code defined on a many-body system of qubits. And that's sort of the setting that we'll be considering here. So generally, ideal error correction requires high weight measurements, and these are difficult to access experimentally. So in the case of the toric code, these are 4 local measurements. And so our question is, what can we do with sort of the more local interactions that nature gives to us? Okay, so that's sort of our broad motivation. And to just give a little bit more background, in this talk, I'll speak about subsystem codes, which are a particular type of error correction code, Free-Fermion solvable spin models, which is the sort of narrow physical setting that we'll be looking at. And also I'll argue that the natural sort of language in which to speak about these error correction codes is through graph theory. And then I'll go on to speak about some of our results. So these results involve bosonizations, extending this language to the translation invariant setting, and I'll introduce the checkerboard-lattice code, which is the code that is sort of a great sort of fruit fly example of all of these concepts. And then I'll close with a numerical search that we've performed to sort of search for suitable codes. All right, so a subsystem code, one can think of it, or at least in the setting that I'll be speaking about, involves a set of terms, or a general error correction code involves, you can think of as a set of terms in a Hamiltonian, which suppress errors outside of a logical code space. So people sometimes speak about error correction as a set of measurements, measuring elements of a group. Here, we're going to be in sort of the error suppression Hamiltonian framework. So we're thinking about a Hamiltonian that I can just turn on. I can leave it on running arbitrarily long, and the excitations away from the ground space of this Hamiltonian are thought of as errors. And we want to energetically suppress these, given that we can only sort of keep our Hamiltonian, turn our Hamiltonian on with so much energy. So we can't make this Hamiltonian arbitrarily strong. And as I said, we'll be in the framework of many-body qubit operators. So sigma j is a Pauli operator, and E is the set of operators which are included as terms in this Hamiltonian. So it's E for what will be the edges of a graph. So sort of thinking ahead in terms of the notation, and this is possibly an overcomplete set. And so in a stabilizer code, the sigma j operators all commute, and the logical states are all the +1 eigenstates of the sigma j operators, the mutual eigenstates of the sigma j operators, because they all commute. And we want this logical space to not be trivial, so we cannot include the minus the identity in our stabilizer group. And right, so because these all commute, we can find a mutual eigenstate for all of them, our mutual eigenspace. So in subsystem code, while these stabilizer generators are well understood, they're generally very high weight. And so what we can do is we can circumvent this high weight criterion using subsystem codes. And so in a subsystem code, the generators of the group, the gauge group of this error suppression Hamiltonian, are non-commuting, And logical states consist of the sort of logical subspace in tensor product with a set of gauge qubits. And G here is the ground state of the Hamiltonian on the gauge qubit. So I want to suppress excitations away from that ground state. And we need the Hamiltonian to act trivially on the set of logical space. So yeah, the Hamiltonian acts as the identity on logical space and acts only non-trivially on G, the set of gauge qubits. And so this generally requires, in order to understand the behavior of this Hamiltonian, generally requires brute force diagonalization of the Hamiltonian. And so that can be very hard depending on how non-trivially interacting your Hamiltonian is. But our question is, can we sort of circumvent this problem, or can we use exactly known, previously known exact solutions to extract the behavior of this Hamiltonian? Right, so I'll now be talking about one specific family of exact solutions called Free-Fermion solvable spin models. You know, just to kind of get things started, I'll consider a sort of conventional one-dimensional example. And so H1D is a sum of two local terms, XX and YY, on neighboring pairs of qubits in a 1D chain. And this Hamiltonian has an extremely well-known solution given by the Jordan-Wigner transformation. So the Jordan-Wigner transformation identifies the Pallies in this Hamiltonian, or Pallies generally, with Majorana operators. And so the form of these Pallies is Zs, or a string of Zs, extending all the way to the left by convention in 1D. And on the site of sort of interest, the site labeling the Majorana mode, I have either an X or a Y operator. And if J equals 1, then there's no string of Zs. So sort of, this is a schematic meant to show that you generally have a tail, but you may sometimes not. And we can see from their Pauli form that these Majorana operators always anti-commute if their indices are different. And because they're Paulis, they also square to the identity and are Hermitian. And so under the Jordan-Wigner transformation, the Hamiltonian maps term by term to this Hamiltonian of this form, which is a quadratic in the Majorana operators. And so if we just look at this sort of pictorially, we see that the Hamiltonian on n qubits maps to a Free-Fermion model on 2n Majorana modes. So each of these gray circles here is distinguishes a pair of modes, or consists of a pair of modes, and labels a qubit. And the Hamiltonian terms are now mapped to the edges of this interaction fermion hopping graph. So the YY terms are mapped to sort of hopping that are 4 sites apart on this linear chain, and XX terms are mapped to sites which are next to each other. And so since this is a quadratic in the Majorana operators, we can write it as a contraction of the Majorana operators on a coefficient matrix. So this is the exact form of the coefficient matrix for the first 4 modes. And I've pulled out a factor of 2. And note that this coefficient matrix must be anti-symmetric because the Majorana operators all anti-commute. So in order to be non-trivial under the canonical anti-commutation relations, this single particle Hamiltonian, which is this coefficient matrix, needs to be anti-symmetric. And again, there's a factor of 2 because we are double counting products of Majorana modes because of the anti-symmetry. And so this gives us the Hamiltonian in a nice quadratic form where H, bold H, is the single particle Free-Fermion Hamiltonian. And so then what we can do is we can exactly diagonalize the Hamiltonian using an exact diagonalization of this much smaller matrix, H, little h, which is 2n by 2n. So from the canonical anti-commutation relations, we see that the Majorana modes individually transform as covariantly under conjugation by exponentials of the Hamiltonian. And this covariant transformation maps a given Majorana mode, say gamma mu, to a linear combination of Majorana modes gamma with coefficients given by the exponential of the single particle Hamiltonian. So because the Hamiltonian itself is an anti-symmetric matrix with real values, the exponential is an orthogonal matrix, so it's a member of the group SO2n. And so what we can just do is find the matrix. In this case, I'll call that e to the 4w. which is the orthogonal matrix that block diagonalizes the single particle Hamiltonian. So because single particle Hamiltonian is antisymmetric, there's always a block diagonalization of it. And then we take its Majorana representation and we conjugate the Hamiltonian in the Majorana picture by the Majorana representation of the diagonalizing matrix. And so what this does is it maps the Hamiltonian to one where the Majorana modes only pair up sort of with each other, and you don't see any other interactions outside of these pairs. And so when we look at this under the Jordan-Wigner, back in the original Pali picture, this gives that the Hamiltonian is conjugated and mapped to a sum of sigma z's with some coefficients. So essentially the spectrum is again sum of eigenvalues of sigma z with some weights, and these weights are the Williamson eigenvalues of the single particle Hamiltonian. Right, and so that's the entire sort of route for the exact solution of the Free-Fermion Hamiltonian. Its spectrum is given by sums and differences, the Williamson eigenvalues, which are parameterized by a bit string, and the eigenstates are given by acting a computational basis state, or acting a given unitary on the computational basis state. That gives us the full solution of this Free-Fermion solvable Hamiltonian. And so I just want to pull away some sort of interesting features of just this one-dimensional model. So at the top half of the slide, we have what we know already, the sort of exact solution method. But so when n is odd, when the number of qubits in this model is odd, this model has a pair of logical operators, well, logical-like operators. And these are the product of all x's, and I'll call the product of all x's the logical x, and the product of all z's the logical z. And note that the x and z logicals anti-commute with each other because n is odd, so they have odd many anti-commutations with each other. And they commute with the Hamiltonian because the Hamiltonian terms appear in pairs. So, or rather, the Hamiltonian terms are exactly weight 2. So, if the Pali types are different from the logical Pali types, then the anti-commutation happens twice, so they commute. And also because they're exactly weight 2, I can't use products of these to make an odd weight product of Pali. So I cannot generate these logicals from products of the gauge generators in this 1D example Hamiltonian. However, even though it has a pair of logical-like operators, they can be cleaned, which is to say that I can multiply these logical operators by Hamiltonian terms to sort of push all the non-trivial parts of these logical Palis onto the boundary. So for example, for n equals 5, I can take logical x, which is the product of all x's on the 5 qubits, and multiply them with the pairs of x's on all of the other qubits except for 1, giving me only x1. So what that means is that an x1 local x1 error on, say, the boundary of the code will have non-trivial support, will have a non-trivial action on the logical space. It will have it will not be independent of the logical operator. So in trying to correct this this error, I may inadvertently introduce a logical error. And so it seems that 1D is sort of insufficient for our purposes to avoid this problem. So we asked if we can circumvent this problem by going to 2 dimensions. And so the answer is yes. And so I'll just give a sort of brief overview of the result before I continue. So we consider this code called the checkerboard-lattice code. And so this is a code whose gauge generators are shown in sort of the top half. These 8 panels are the gauge generators, A through H. And it has weight 6 terms, so it's unfortunately not a low weight Hamiltonian, but it is Free-Fermion solvable. And its terms sort of consist of these asymmetric bond operators on the surrounding the vertices of this unusual looking lattice, which I'll explain. And it's symmetric upon switching X with Z on these operators A and B. It has loop-like stabilizer operators, which are loops of Y operators on the faces or the cycles of the graph. And it also has 2 pairs of logical operators, or 2 logical qubits. And I've just shown one here. So the other 2 are related to these A and B by rotating the entire code by 90 degrees. And so it has a string-like logical that winds around, this is on periodic boundary conditions, winds around the handles of the torus. So it has a Y-like logical winding around the handle of the torus, and then a Z-like logical, well, another sort of funny looking logical winding around the other direction. And this logical sort of explicitly breaks the translation invariance over a single unit cell out to 2 unit cells of the lattice. So we require that the torus have even boundary conditions similar to our one-dimensional example. And so this Hamiltonian has a free-fermion solution, and the mapping takes the Hamiltonian gauge generators and maps them to 2 copies of the square lattice. Free-fermion hopping terms on 2 copies of the square lattice. So there are 2 disconnected free-fermion hopping terms, just as before, but now in 2 dimensions. And unlike the original case, the earlier case, the logicals here cannot be cleaned by gauge generators to have constant support. So that's to say that the distance of this code scales linearly with the system size. That's something we can prove. So, right. So this is kind of a funny looking model. And so what I'm going to do for the next couple of slides is just sort of explain what are the tools we use to find this code, and how these tools can be used, leveraged to find similar codes which are sort of suitable for a variety of purposes for error correction. And so to do this, I need to explain some graph theory. So a previous result in the paper that I sort of just pointed to at the top of the talk, the title slide, that we have is that the Hamiltonian has a free-fermion solution if the Pauli terms correspond to edges of the graph, the edges of a graph, such that the edges in that graph are incident if the Pauli terms anti-commute. So to maybe just kind of give some motivation for this, if I have 2 quadratic Majorana operators, mu nu and eta z, then the commutation between these 2 quadratics incurs a sign or a phase factor, which is -1 if these 2 operators overlap at a mode. So if one of these pairs, one element of one of these pairs is equal to an element of the other pair, then they incur a minus sign. And so we can think of these 2 pairs as labeling edges of a graph, and we say that these operators anti-commute if those edges are incident. And yeah, so we have edges E1 and E2 consisting of the 2 pairs of modes. And to sort of develop our graph theoretic language a little bit more, the sort of main tool that we use here is what's called the frustration graph of a Hamiltonian. So given a Hamiltonian in the Pauli basis, as I mentioned before, its frustration graph is a graph with vertices corresponding to Pauli terms in the Hamiltonian in that basis. And the vertices are neighboring in the graph if the corresponding Pauli terms anti-commute. And so the claim of this previous result is that we can injectively map the terms in H to free-fermion terms if and only if the graph is what's called a line graph. And so this is the sort of graph theoretic criterion that we need in order to say, given a Hamiltonian H, we can map each term in H to a pair of modes. So this kind of avoids the question of how do you define a single mode, which is something that the Jordan-Wigner transformation gives you, but it generalizes to higher dimensional models and other settings. So to define a line graph, the line graph of another graph called the root graph is the graph whose vertices are the edges of the root graph, such that vertices in the line graph are neighboring if their corresponding edges share a vertex. So here, the graph R is what's called the root graph. This is just a cycle with some dangling edges. And what we do, I guess, sorry if this is too small to see, but we identify each edge in this graph with a vertex of another graph. And these vertices are neighboring if the edges are incident. And so taking the line graph of this graph R here results in a graph that looks like this. And so the question is, when can we do this process in reverse? So when can we, given a frustration graph of a Hamiltonian, when can we identify it as the line graph of some other graph? And this, prescribes an injective free-fermion mapping from the Hamiltonian terms to free-fermion terms. And I don't give it too much here, but you can see our paper. Line graphs are extremely well characterized, and they can be efficiently recognized. So there's a wide variety of different ways to characterize line graphs in terms of, say, forbidden induced subgraphs or clique decompositions, and there are algorithms which can efficiently, given a graph, recognize if it's a line graph. So the theorem that we gave in that paper is to say, given a Hamiltonian in the Pauli basis, there exists an injective mapping from Pauli terms to pairs of Majorana operators, such that the Pauli terms satisfy the same commutation relations as the Majorana operators, if and only if this graph is the line graph of the frustration graph of H is the line graph of some root graph. And then the root graph you can kind of physically interpret as the hopping graph of the Fermion model. And so what'll be sort of the most important thing here for us is what we call root graph symmetries. And so these are a set of symmetries that every Free-Fermion model is sort of guaranteed to have by this characterization. So what we're sort of asking for are elements in the error correction code language, which are in the center of the gauge group. So if I say that H is a sum of terms which are the generators of a gauge group of a subsystem code, then the center of the gauge group is elements which are products of terms from the Hamiltonian that commute with every term in the Hamiltonian. And so we ask, what are these products? And these can be derived from graph theory. So in this language, the products are the elements of the binary kernel of the adjacency matrix. And these come in sort of three different flavors. The first is one that I probably won't talk about, which is called twin vertices. So this is a trivial set of symmetries that exists when two Paulis have exactly the same neighbors in the frustration graph and commute with each other. So their product is always a symmetry of the model because they have all the same. If one of them anti-commutes with a Hamiltonian term, then the other one does as well, and so their product always commutes. And if their product is non-trivial, then that's a symmetry of the model. The other two are sort of more interesting from a graph-theoretic perspective. One is called, so cycles of the root graph is one set of symmetries. And this gives rise to kind of a topological way of viewing the center of the gauge group. And the other is the fermionic parity operator, which is also a symmetry of Free-Fermion models. So one useful property of the adjacency matrix of a line graph is that it has a factorization over over the binary field. So the adjacency matrix factorizes as BB transpose, where B is the incidence matrix of the root graph. So it's the binary matrix whose, in this case, whose rows are labeled by the vertices and whose columns are labeled by, whose rows are labeled by the edges of the root graph and whose columns are labeled by the vertices. And the element of this matrix is 1 if the vertex j belongs to the edge I and it's 0 otherwise. So this factorization is very useful. And so as I said before, sort of graphical symmetries correspond to vectors, which are in the binary kernel of A. And so there's only two possible ways this can happen. Either this vector is in the kernel of B transpose. And so what that means is that it's a subset of Pauli terms, which when mapped to a subset of edges in the root graph, the edges have even degree. So V is a subset of even degree, is a subgraph where all the vertices have even degree, and that's either a cycle or a union of cycles. And then the other case is where B transpose V is mapped to an element which is in the kernel of B. So B transpose maps V to an element in the kernel of B. And because B is an incidence matrix, this gives that B is mapped by B transpose to the all ones vector. And this is called the fermionic parity operator. So we can actually think of B transpose in a way as being the operator which maps subsets of Hamiltonian terms to products of Majorana modes. And so if B transpose maps a product of Hamiltonian terms to the all ones vector, that means that it's the product of all the Majorana modes, and it's therefore the fermionic, what we would call the fermionic parity operator, which is always a symmetry of Free-Fermion models. So then in our Free-Fermion solution, the question is, how do we incorporate these symmetries? And so what I've said so far only defines the Free-Fermion solution up to signs in the mapping. So while I've said you can injectively map Pauli terms to quadratics in the Majorana modes, this does not necessarily tell me how to choose a sign of the image of a Pauli term. So if I exchange the two modes that I identify a Pauli with, that effectively changes the sign of the hopping term. And this also corresponds to, you can think of this as an orientation of the root graph, and it's not fixed by the commutation relations between the Paulis. It's fixed by sort of the one-sided multiplication relations between Paulis. And so we actually choose this orientation when we fix the eigenvalues of the cycle symmetry. So there are always a subset of cycle symmetries for these models. And by choosing those symmetry eigenvalues, we obtain constraints which tell us when a subset of Paulis multiplies to plus or minus the identity, and that sign tells us both the eigenvalue and will be determined by the orientation or the signs of these Majorana modes. And then just as kind of a last little technical caveat, if the parity operator, when I take the spin model version of the parity operator, if that happens to be proportional to the identity, what that means is that only a fixed parity subspace of a fixed parity subspace of the Free-Fermion model is sort of physical in the spin picture. So when finding the solution of the Free-Fermion model, we need to restrict to a parity sector of the Free-Fermion Hamiltonian. Okay, so maybe that's a lot of background, but now we can use these graph-theoretic tools to show how this helps us search for suitable Free-Fermion subsystem codes. So the first question we maybe want to ask is, if we're given a graph G, suppose it's the line graph, and so we're guaranteed a Free-Fermion solution, how do we find a nice spin model whose frustration graph is G? And so this is a question of finding a nice Bosenization for the model, or representation. And this will also determine sort of the logical content of the code. There's a systematic way to do this. So given this graph, we take its binary adjacency matrix, and we write it as a binary sum of adjacency matrices of complete tripartite graph. So a tripartite graph is one where the vertices can be given three colors, such that any vertex in a given coloring class neighbors all of the vertices in the other two coloring classes, and none of the vertices in a sixth coloring class are neighboring to each other. And when I say three-partite, I mean at most three-partite. So I can also allow for two-partite, bicolorable, complete bipartite graphs. So just two examples that we consider in the paper are the examples of decomposing the adjacency matrix into single edges. This is what we call the fiducial Bosenization. And a Bosenization of this form exists for every graph, even if it's not a line graph. And then the other sort of next most interesting Bosenization is called the Kataev Bosenization. And so this is where we decompose the frustration graph into triangles or cliques, which are also three-partite and complete three-partite graphs. So just to sort of give an example, we have this frustration graph that we showed earlier, and to find the fiducial Bosenization of this graph, we decompose it into the binary sum of all of its edges. So that's to say we identify each edge with a qubit, and then what we do is we say, for each vertex in the graph, which is the Hamiltonian term, we find the Hamiltonian term realizing that vertex by assigning either an x or a z to each of the qubits adjacent to it, depending on, we orient each edge and we identify this term depending on which of the two sides of the edge is adjacent to that vertex. So in this case, it gives kind of a 12 vertex model or 12 qubit model whose interactions are at most 4 local, because in this case, you're guaranteed that the weight of a given term is always the degree, the maximum degree of, well, the weight of a term is always the degree of that vertex. So we have 4 degree 4 terms, which are the four full or local operators here. And we also have, 2 terms. And so the 4 local terms, we have to choose the Paulis that are on these terms by such that whenever these 2 Paulis overlap at a qubit, they anti-commute, which enforces the commutation relations between those terms. And then the remaining ones, the 2 local terms, are ZZ on every qubit there. And so if we can decompose it into triangles instead, which in this case we can, which is what we call the Kitaev bosonization, named after the Kitaev honeycomb model, then in this case we only have 4 qubits, 1 assigned to each triangle, and this gives a much more compact realization of this frustration graph. So here we now have, again, 8 terms, but now each of them is always 2 local. And it's maybe easy to see that if the frustration graph is the line graph of a degree 3 root graph, then we can always find a bosonization of the Kitaev type where all of the operators in the Hamiltonian are 2 local, or at most 2 local. So you also have some 1 local terms here because these Z's belong to only 1 triangle. And so we see like a dramatic improvement depending on the type of bosonization you use. So it's possible that, there are just interesting sort of graphs with sort of nice decompositions that are much more compact than others. And this is essentially, I guess, the problem of finding good fermion to qubit mappings. If I start with a fermion model and I want to map it to either a compact or a minimum number of total qubits spin model, this is the kind of thing you want to do. And so sort of similarly to the line graph decomposition, bosonization also gives a factorization over Z2. So there's a factorization of the binary adjacency matrix of the line graph, where this binary factorization now, instead of being the incidence matrix of the root graph, is a matrix with some kind of maybe funny looking form, but essentially each of the columns of this graph are grouped into sets of 3, and the binary vector that's present on that set of 3 columns depends on the Pauli which is present at a given term. So what this says is that I have, say, 0, 1, 1 if there is an X present on qubit J in term I. And this gives a way of realizing the frustration graph adjacency matrix as a factorization of the sort of bosonized binary adjacency matrix. And upon choosing a bosonization, we have logical operators, which are elements of the gauge group that are not, elements of the center of the gauge group that are not in the gauge group itself. And so we can state these linearly algebraically as vectors that are in the kernel of B itself, so commute with every term in the Hamiltonian, but are not in the image of B transpose. So they're not the product of anything from the gauge group. And so choosing a bosonization is kind of an art to find logical qubits. And just one more thing that I want to mention that we deal with in this paper is how to describe these models in terms of a sort of compact description when you have translation invariance. So here's an example of an infinite translation invariant graph. This can be extended to periodic boundary conditions as well. So translation invariant graph in 1D has a block topoless adjacency matrix. So it has bands going along the off diagonals, and it's symmetric. So the off diagonal bands are related by a transpose when they're symmetric bands. And so we can map this to a compact form. Say this is formally an infinite dimensional matrix. We can map this to a compact form by describing A as a Laurent polynomial valued adjacency matrix. And so we think of X as being an indeterminate, which describes a translation by a unit cell. And so X to the K is a translation of K unit cells. And so formally, we just write that the Laurent polynomial value matrix A of X over this field Z2, where X bar is the inverse translation of X. This Laurent polynomial valued adjacency matrix is the sum of all the band matrices with a polynomial weight, with a monomial weight. And so, for example, for this infinite dimensional graph, this is the sort of nicely compact unit Laurent polynomial valued adjacency matrix. Because the unit cell only has 2 vertices in it, this is a 2x2 matrix. And we see that, so for example, the diagonal elements are not necessarily 0 because the vertex 1 here neighbors x and x bar. And then it also neighbors 2. And so we can include extra dimensions in this formalism by adding extra variables. And so I'll just sort of summarize the results we have in this direction. So we give an algorithm which can efficiently recognize line graphs by only looking at the Laurent polynomial valued adjacency matrix over a unit cell. So if we're given, formally an infinite graph, we don't have to check a very large section of the graph to verify that it's a line graph. We can recognize it just by looking at the unit cell. And then also something which is maybe nicely what you would expect is that the adjacency matrix, the Laurent polynomial valued adjacency matrix, has the Bosenization factorization I alluded to before, with kind of the Laurent polynomial valued Bosenization matrices altered in exactly the way you would expect, which is I take, instead of VB transpose, I take VB dagger, where the dagger is given by the conjugate, the transpose and conjugating the variables, that is replacing x by x bar. Okay, so these are sort of the sort of fiducial tools we've used to perform a search over Free-Fermion subsystem codes. And so I just want to describe how the checkerboard lattice code fits into this formalism. So here are the logical operators of the checkerboard lattice code again. This code, the gauge generators are given by the fiducial Bosenization on the line graph of the square lattice. So this is where this lattice comes from. It's actually the line graph of the square lattice, and it's degree 6 because each of the edges in the square lattice has 6 neighboring edges to it. Or alternatively, you can see that each of the degree 4 vertices in the square lattice gets mapped to a clique or a complete graph of size 4. And so what's kind of interesting is that for this particular model, replacing x with z on the gauge generators, as I said, there's a symmetry between x and z on the gauge generators. And so this actually gives a second commuting copy of all of the gauge generators. So the Hamiltonian can be written essentially as h0 plus h1, where h0 and h1 commute with each other and are sort of symmetric in that they describe the same set of gauge generators up to a Pauli replacement or a Clifford conjugation. And we end up with an additional set of stabilizers given by y loops on the lattice. And these sort of correspond to the y logical string operators. So the y logical strings are deformed by the y loops. In the different sort of models we've looked at, we haven't really found one where there isn't at least some set of stabilizers that are not made of gauge generator, or sorry, stabilizers that are not mutually commuting. So we always sort of seem to end up with mutually commuting gauge generators outside of the Free-Fermion gauge generators. And then the reason we have these extra logical operators here that break translation variance is because products of these translated by one unit cell, so taking one translation of it and multiplying them, gives the cycle symmetries that I alluded to before for the line graph Free-Fermion solution. But it turns, so while those cycle symmetries are always the symmetry of the Hamiltonian, it turns out that they're also the products in the qubit realization of pairs of symmetries, and those symmetries cannot be made out of gauge generators. So you pick one of them, and the other one is related to it by a cycle operator. Picking one of them gives a logical operator. And so this is sort of a summary of the theoretical tools we have to systematically search over Free-Fermion subsystem codes using graph theory. And so we've looked over a large sort of family of these codes to look for sort of the sort of natural physical criteria that we would want to realize these codes for error suppression. So as I said before, the Free-Fermion symmetry sectors come with these cycle symmetries, and these correspond to orientations of the graph. So unlike the one-dimensional model I described, where there's precisely one Free-Fermion model that corresponds to the solution, in 2D or in sort of models where you have non-trivial cycles, or just cycles, each of the symmetry sectors corresponds to an orientation of the graph. So you actually end up with a family of free fermion solutions, one for each orientation. And so this actually introduces an additional complication, because not only do we have the free fermion single particle gap, but also we have a global gap between different symmetry sectors. And so this is related to a concept in graph theory called the skew energy. And so what we seem to find is that there's something of a trade-off between how big we can make the single particle gap by finding an orientation where the gap within that single particle orientation is rather large, but also finding a graph whose skew energy gap is also large. And the skew energy gap there's much less known about this. So basically, we essentially ended up looking at several different graphs and looking at their skew gaps and also their inter single particle gaps. They're within a fixed sector single particle gap. And so here we have two one-dimensional models. This is the ladder model, which is a ladder graph, and it has two orientations, one of which has a large gap and one of which doesn't. This is the so-called elementary orientation of the graph. And then this is the honeycomb ladder graph, I believe. And you can see that two different orientations also give two very different looking single particle gaps. So we summarized our sort of heuristic findings in this table. So there's two directions in which we can make the gaps more difficult. We can either increase the dimensionality, which makes it harder to find large gaps in these models, or we can change the coordination or the degree of a regular graph from odd to even. And so here are sort of all the families we looked at and how they fit into these two sort of partitions. And we also have a set of graphs we've looked at in the way that their single particle gaps behave. And so, as you can see, some of these graphs, it's well known what their ground state orientation is, the orientation that gives you the ground state of their global energy, but others it's not known. And there's a theorem that says that if you can find an orientation where all the even cycles are oddly oriented, then that is the skew energy maximizing or ground state energy minimizing orientation of the global graph. But you can't actually even find these even for two-dimensional models. But nevertheless, these models have the property that for the orientations which maximize the orientations where all of the plaquettes are oddly oriented, that is, there's odd many edges going one way against the orientation of the graph and odd many edges going the other way around each plaquette. Those tend to also minimize the skew energy. Right. So with that, I'll just conclude. In this work, we looked at a set of codes that we call Free-Fermion subsystem codes, searching for a set of graph-theoretic sort of tools to find and characterize these codes. We introduced the checkerboard-lattice code, which is a code with non-trivial logical operators, solvable over two distinct copies of the square lattice on a torus. And we provide a sort of set of numerical heuristics to search for these codes. And so in future work, we're planning to continue the search for interesting codes in 2D and 3D. Another really interesting open question that we have is, can this exact solvability be exploited for decoding? So with that, I just want to acknowledge my co-authors, Stephen Samia and Alicia Klar, and also acknowledge our funding agents. And I also want to thank you once again for coming to the talk, and I'll take any questions now.
Yeah, thanks a lot, Adrian. Yeah, that was a really interesting work. Let me see if there's any questions on live first.
And it has two orientations, one of which has a large gap and one of which doesn't. This is the
there's any questions on live
graph,
first.
and it has two orientations, one of which has a large gap and one of which doesn't. This is
Probably
encoded.
not any. Okay. All right. Yeah. So what are the parameters of these codes? So for the checkerboard lattice code, you said distance is linear.
That's right. Yeah. So what we do to prove this is, as before, right? We said that we could clean the code logical operators by, in the 1D case, you can clean the logical operators by multiplying by pairs gauge generators, which have weight 2 terms. So here, what you can do is you can just look at these funny logical operators on just say the vertically oriented edges of the horizontally oriented logical operator. So maybe it's a little bit hard to see, but here we see that all the vertically oriented edges are X type. And so it turns out that there's no gauge generator that can generate a single X only going the other way around the handle of the torus. So I can't actually generate a single X on just one vertical edge without introducing another X or a Z operator on the adjacent vertical edge. So I can move them around with some stuff that happens with the gauge generators that are some like residual action by the gauge generators, but I can't completely eliminate them. And then with the Y operators, it's sort of maybe easy to see that because the only way to eliminate Y operators is to make cycles of Ys, a cycle of Y that winds around the handle of the torus, and we can only make homologically trivial cycles of Ys. We can't remove these. So yeah, that's right. So the distance is linear.
Right. And then you know the stability, you get the syndrome measurement as well from the bosonization.
That's right. So the syndrome measurement, the stabilizer group of these models, as I said, one sort of sector of that is the Y loop stabilizers, and then the other is products of the Hamiltonian gauge generators around cycles in the graph. And so these kind of give, that's right, so these give the syndrome operators. And so the kind of idea that we had with exploiting the exact solvability to find good decoders is to essentially say, if we know the complete spectrum of the model and we expect the certain types of errors to be energetically suppressed, we want to design a intelligent prior for the kind of noise that we want to assign to a given syndrome measurement. And so that's what we're thinking about now.
So for like what you show with the example of Kitaev graph, so that's the two bodies are the syndrome measurements, right? Or is do
you mean
this one? Yeah.
So this generally what's going to happen,
like Hamiltonian terms.
That's right. Generally what's going to happen is if you can do this with fewer qubits, you're going to have fewer logical qubits. There's a minimum number of total qubits you need to bosonize any graph. And that number is, for any line graph, I should say, and that number is the, essentially scales as the number of vertices in the root graph. It's like the number of vertices minus a constant divided by 2. So it scales as the number of vertices in the root graph. This root graph has 8 vertices, but you might subtract the constant divided by 2. In this case, you need at least 3 qubits to find the bosonization of this graph. So this does it in 4, but it also has that symmetry. So the products of XXYY, XXYY is Z on every qubit, and that's the symmetry of the model. And you can also make that by taking the products of all the Zs on all the single qubits. So you have these extra symmetries that account for qubits that you end up projecting out when you restrict down to a symmetric subspace.
I see. And for terminology wise, it's called bosonization just because you combine So the original, which direction I'm going is from fermions to,
That's right.
well, initially I just have a graph. And then
so we sort of adopted this question, or sorry, we sort of adopted this this terminology from the literature surrounding embedding fermion models into qubit models. But you're right. So we don't a priori have a free fermion model just given a graph, but we essentially finding the qubit embedding of that model. We call it a bosonization because really what we're interested in is finding a qubit embedding of a free fermion model. But this is essentially a term from the literature.
Right. Okay. Yeah, so this is very interesting. So like I'm not familiar with subsystem codes. So when people design subsystem codes before, like how do they, like, I don't know, generally figure out the codes that they want? Because here the way that the narrative in this slide is that the gauge degree of freedom should be a ground state of Hamiltonian something, right? Then if it's easy to, right, you said that typically if people want to know anything, they probably have to brute force just diagonalize the Hamiltonian. That
right. But you can say a lot without doing that.
Right.
But right, generally you do need a brute force diagonalization if you don't have an exact solution. But there are other reasons to consider codes that are not exactly solvable as well. So you might care about like gauge fixing and how you might be able to implement logical operations, like if you want to be able to implement them transversely, for example. Yeah, and so essentially it's sort of the art that's we're trying to sort of motivate is that can you find codes that are useful in that sense while also having this additional property of being free fermion solvable. And we were sort of at the beginning of this project not really sure whether even there would exist a code that just even had like topological qubits and is also free fermion solvable, because a lot of the examples that we looked at were either one or the other, but right, essentially, like it was surprising to us that there's an example that exists that also. So I should also remind you that the logical operators, right, cannot be made of gauge generators. So another thing that can happen is, so when we talk about this in the paper, is that you can essentially find a kind of like clever refactorization of the degrees of freedom where you have a free fermion model on one subset of the gauge qubits, and then essentially like a toric code on the other subset or something. And the reason that's a problem is that any problems that the toric code is going to have, there's just now an embedding of those. So the toric code, for example, has there's no additional excitation energy. So if I want to, if there's an error that happens once on the toric code, that creates a pair of excitations, but then those pair of excitations are free to move around.
Right.
So in the code that I described, this can also happen. It's just that the excitations, in order to move an excitation, as a global process that costs no energy, but you have to just get over like maybe a small energy barrier, but globally the energy doesn't change after you've gotten over that barrier. So there's maybe like constant weight errors that will cause excitations to move around freely. And so that code is sort of runs into that problem. So what we're sort of surprised by is the fact that there's an example of a code where essentially it is similar in the sense that like both sets of gauge qubits kind of refactored in an interesting way, but also both of them are suppressed by a Free-Fermion model. And then we have these extra additional Y loop stabilizers.
I see. So I guess, well, there's no other question. My final question, the $1 million question. So do you see in the future that actual implementations adopting this kind of codes? What
well,
do
so
we?
I'm not an experimentalist, but
Right.
so I don't really know. But I think it's potentially promising for a number of reasons. One is that you can maybe access lower weight terms. The other is that if in an experimental setting I have the option or the ability to maybe just turn on some terms and leave them on, but I can't turn them on and off arbitrarily, this might be sort of suitable for that. The other thing, which I didn't talk too much about, is that if I have kind of parametric errors in my Hamiltonian, so if I turn on my terms and I don't have complete control of how strong they are, what's nice about this family of Free-Fermion solutions is that it will still be solvable even if those, I can't, make all those terms have coefficient 1, say, but it still has that Free-Fermion solution property. So, there's a number of reasons I think it's appealing, but yeah, it's a little bit, it's unknown at the moment.
Right. Yeah, actually, yeah, that is really interesting. So like for surface code, people are doing it now, as I don't understand, because it just requires a relatively low weight syndrome measurement. Right? I don't know how. I never read experimental paper. I don't know how they measure it for body terms, but yeah. But then the other parameters are kind of bad. I think the rate or something like that, which is now like why like theory people are thinking about the low density parity check code.
I see.
Which I think has a better rate, but I don't remember on the top of my head. So I guess maybe these parameters, yeah, I'm not sure how it's compared to surface code.
You
Well, I
mean
guess
the code distance parameters? So this has a
yeah.
rate of asymptotically approaching 0 because it has a constant number of logical qubits, but it has an extensively large distance. So it has a distance of order L, where L is the linear dimension of the lattice.
So that is for surface code or for this checkerboard.
Sorry, say that one more time.
Is that for surface code or this checkerboard lattice?
For the checkerboard lattice. We thought a little bit about, I guess, like hyperbolic lattice codes. That's something Alicia in particular has done previous work on, but that's also kind of an open question for us at the moment.
Right. And for the decoding scheme, do you have to like come up with something completely new, or I don't know, or like you can use stuff that's...
I don't think it needs to be completely new, but I think so. Even in the case of, say, like the one-dimensional Kitaev wire, which is just a sort of it's a Free-Fermion Hamiltonian that you can implement as a Bosonisation of something, but kind of in its most conventional form, it's just given as a Free-Fermion Hamiltonian. I think even just understanding how that particular Hamiltonian interacts with different noise models is a non-trivial question, because so the noise, it's very easy for the noise to break the integrability, and so I think this is maybe another sort of appealing property of these codes, is that if you have the ability to design code such that you know what your noise is, or you know that there's some strongly biased noise in a particular direction, like you could in principle say, I just want to design my code such that this type of noise doesn't break the integrability that the code has. So if my code is like strongly biased in the X direction, maybe I can find a code for which X type noise doesn't break the integrability. But yeah, so understanding even how how a realistic noise model might interact with these codes is kind of a non-trivial problem. And then, the other very non-trivial part is sort of the plethora of orientations, like the different symmetry sectors that these, right? Like it's one thing to solve a Free-Fermion model, but it's also another thing to solve all 2 to the n, 2 to the, k Free-Fermion models where each k corresponds to the orientation of the graph. So our hope there is to kind of look for, I think, aggregate sort of properties of all of the different spectra and see if, there's something there we can use.
All right. Yeah, thank you again for coming and giving a talk, accepting the invitation. Yeah, I think this is a good time to stop because it's 11 3 past 11 over here, and this was like 9 p.m. over there.
Yeah, that's right.
All right, yeah, so thanks everyone for everyone who's watching online. And there's if you're watching online, then there's this survey if you're satisfied or what you're not satisfied with the Colloquium series, and if you have time, please fill that in. So I guess we'll call it a day for the Colloquium today. นะครับโจก็
Great. Thank you very much once again.
Yeah, we can go to the backstage now.